GenAI versioning goes far beyond code. Models, prompts, RAG indexes, datasets, and configuration all shape system behavior. When teams track those changes together, they can reproduce results, debug failures, audit risk, control cost, and release safely. So far, we've built the foundation: how GenAI systems are architected, integrated, deployed, and automated. Now we shift from delivering the platform to controlling the assets that shape its behavior: prompts, datasets, models, and configuration. The key question becomes, which exact version produced each production result? In traditional software, versioning usually means tracking code and infrastructure. In GenAI, that is not enough. The final response can change because of a prompt edit, a new model release, a changed embedding model, refreshed documents, different chunking, or a runtime parameter. None of those require a code change. If these inputs are not versioned together, teams cannot reliably reproduce an answer, diagnose a regression, or roll back safely. GenAI versioning is system state versioning, not just code history. Production GenAI behavior is shaped by many assets, not just application code. Prompts include instructions, templates, examples, tools, and defaults. Models include provider, revision, context limits, inference settings, and safety configuration. RAG includes documents, chunking, metadata, embeddings, and index snapshots. Evaluation includes test sets, rubrics, labels, golden answers, and automated judges. The goal is traceability. When an answer changes, you can identify which asset changed, roll back safely, and compare versions fairly. Treat every prompt as a production artifact, not a loose text snippet. A prompt release should capture the system instruction, developer guidance, user template, response format, and examples used to shape behavior. Those examples matter. Changing one can shift tone, reasoning style, or accuracy. Also, version model settings such as temperature, max tokens, top P, tool rules, and stop sequences. That way, when an output changes, you can tell whether it came from the model, the template, the examples, or the configuration. Prompt changes should move through a release process just like software. High-impact prompts should start as drafts, then pass peer review, automated regression tests, adversarial checks, and safety or compliance review before staging. In staging, confirm that the prompt still meets accuracy, tone, and policy expectations without breaking downstream systems. Then promote it to production with an owner, release notes, version history, and compatibility constraints. Keep experiments separate from approved prompts, and keep rollback ready if behavior drifts. When a production answer looks wrong, we use GPTX is not enough. You need a reproducible fingerprint of the run: provider, model name, revision, endpoint, deployment ID, and region. Capture what that model supported at the time, including context size, multimodal input, tool calling, and output formats. Then record inference settings such as temperature, token limits, safety filters, and moderation rules. Providers can change versions, prices, latency, and policies. Tracking these details makes model behavior auditable instead of mysterious. Model upgrades are production migrations, not simple configuration changes. A new version may improve quality while still breaking JSON formatting, tool calls, tone, latency, or safety behavior. Deprecation also creates a deadline. If your application depends on an unsupported model, reliability becomes a business risk. Cost can drift as well because pricing or tokenization may change even when traffic stays flat. Before switching, compare candidate models across quality, P95 latency, cost per request, context window, schema adherence, and safety pass rate. Then migrate deliberately with rollback paths. An embedding is the output of an entire pipeline, not just a model call. Changing the provider, dimensions, tokenizer, or model version can make vectors incompatible. The same applies to cleaning rules, chunk size, overlap, split logic, normalization, and language handling, because those choices decide what text gets embedded. Metadata needs versioning too, since filters, permissions, and ranking depend on consistent fields. Any meaningful change is a compatibility event, so plan for partial or full reindexing instead of silently mixing incompatible vectors. Your vector index should be treated like a deployable artifact, not a temporary cache. Before major changes, snapshot production so you can roll back and investigate differences later. A useful version record captures source documents, embedding model, metadata schema, distance metric, ANN algorithm, shards, replicas, namespaces, and filters. Label versions clearly across development, staging, production, and historical snapshots. Build new indexes as candidates, validate retrieval quality and operational behavior, then promote them with a controlled traffic switch. For ongoing change, choose the right strategy. Incremental updates, full rebuilds, blue-green deployment, or backfills when historical data needs correction. When RAG performance changes, you need to know whether the system improved or the ground shifted underneath it. Version the source corpus with document hashes, source URIs, permissions, ingestion time, and transformation logic. Version the evaluation data as well, including test IDs, labels, expected behavior, rubrics, evaluator settings, and ownership. Keep separate benchmark sets for regression, safety, factuality, retrieval quality, and business tasks. Most importantly, compare experiments against immutable dataset versions, so model, prompt, and retriever changes are measured fairly over time. Reproducibility in GenAI is less about replaying magic and more about preserving evidence. For any production answer, capture the full request context, user input, prompt version, model version, parameters, retrieved chunks, tool calls, filters, and guardrail decisions. Then connect that evidence to what happened afterward, including parsing, safety checks, evaluation scores, and human feedback. Exact byte-for-byte reproduction may not always be possible, especially with changing models or non-determinism. But a well-kept trace lets teams reconstruct the reasoning path, explain outcomes, debug failures, and defend decisions during audits. Lineage turns GenAI operations from guesswork into evidence. Every response should connect back to the prompt version, model configuration, embeddings, index, source data, deployment, and evaluation run. Keep that identity intact through CI/CD, runtime traces, logs, dashboards, and reports. Then, when quality drops or an incident occurs, teams can ask precise questions. Which release changed? Which retrieval assets were used? Which users were affected? And whether rollback is justified. Strong lineage also makes audits, A/B tests, and regression analysis faster because the relationships are already captured. Versioning is an ecosystem, not a single repository. Git can track code and prompt manifests. Object storage can preserve datasets. Model registries capture model metadata. Vector database snapshots freeze retrieval indexes. The key is connecting these tools through CI/CD. Every build should automatically stamp artifacts with versions, owners, evaluation results, and release notes. Governance becomes part of the workflow through approval gates, access controls, and audit logs. A shared metadata schema ties everything together, so observability and evaluation can trace production behavior back to the release that caused it. Versioning is what makes GenAI operations dependable. Track not just code, but prompts, models, embeddings, indexes, datasets, and configuration. Preserve lineage so you can reproduce behavior, debug incidents, audit decisions, and roll back safely. RAG adds extra moving parts, especially documents, chunks, embeddings, and indexes. Next, these versioned assets support canary staged rollouts, readiness checks, and recovery plans.